Let's get started. Do you see this? When I rotate the sunglasses, the sky gets darker. But why? Why the sky is blue, that's been explained thousands of times on YouTube. But this effect, almost never. It's called polarization. I will show you why the sky is polarized, and once you understand it, things like why the sky is blue or the sunset red become almost trivial. We will even see what the Rayleigh theorem has to do with it. And the best part, you can create your own sky at home with all these effects. This video is made for non-physicists, but I think even physicists will find something new or interesting here. But first, some intro to the concepts we need. What exactly is light? You've probably heard this back in school. Light is an electromagnetic wave. But let's look at what that actually means. Let us try to depict the electric field of light. And take the simplest case. This is a plane wave. I was fighting for a while with a 3D editor to make this, and you can see that it's a mess. At every point in 3D space, the arrow shows the value of the electric field. And yes, it is a wave and it moves. But it's too hard to depict it like this every single time, so let's just look at a card, or even schematically depict it like this, or like this. And what is polarization? It is basically just the orientation, the direction of these electric field arrows. That's all. So here we could say that it is vertical. Very simple. All the ways to depict a plane wave represent just the same physical object. Remember that the electric field, here vertical, is perpendicular to the direction of propagation, here to the right. As you may already know, light of different colors has different wavelengths. For example, red light has a longer wavelength, while blue light has a shorter one. In fact, in real life, light is almost never a plane wave. Laser light is a bit closer to it, but still not perfect because the plane wave is infinite. Usually light looks more like small portions of waves, wave packets or wave trains. They can be presented as a sum of plane waves. For simplicity, we will also depict them as wavy arrows because for us, the exact shape of the packet does not matter. We are interested in polarization. Light can also be unpolarized, meaning it's like a mixture of waves with different polarizations, but the electric fields are still mostly perpendicular to the direction of propagation. When unpolarized light passes through a polarizer, such as polarized sunglasses, it becomes polarized. You can test whether your sunglasses are polarized using a computer or sometimes a phone screen, because the screen emits polarized light, apparently vertical. If you look at the screen through your glasses and rotate them, you will notice that at one angle the screen appears bright, and when the glasses are rotated by 90 degrees, the screen becomes dark because the opposite polarization shall not pass. And the question for genius is here: how could you guess the polarization of the monitor based on this GIF? Write it in the comments. And now another concept we need, a scatterer. Let's imagine a small light source emitting coherent light in all directions. We'll draw a sphere around this source and try to visualize the electric field on its surface. Remember, polarization is always perpendicular to the direction of propagation. Here, the direction of propagation is in all directions, but always perpendicular to the sphere, so the electric field should be tangent to the sphere. It turns out that you can't comb the sphere smoothly. No matter how you try, there will always be some singularities or twists like one shown here. These singularities are just zeros of the electric field in our case. So no electric field and therefore no light propagates in this particular direction. The Rayleigh theorem tells us that a zero will always be somewhere. We cannot avoid it. After all, we are only interested in one particular wave to comb the sphere. You can see it here, and it has two zeros in the poles. This represents radiation from a dipole source. For a dipole source, electric charge oscillates around a certain direction, say up and down like this. This type of radiation looks like what's shown here over time. It can also be depicted in different ways. For example, if you draw a sphere around it and plot the electric field on this sphere, it looks exactly as we discussed. Alternatively, it can be represented as a donut shape, if we just squeeze the sphere proportionally to the amplitude of the field. Note that in the above case, the dipole does not radiate short packets, it's just a single infinite wave. But anyway, why am I even talking about these dipoles? The sun isn't that kind of source. It's incoherent. It radiates wave packets in all directions randomly, and the polarization of the light, that is, the direction of the electric field, varies randomly, still tangent, but completely random at every moment in time. However, what actually acts as a dipole source are the molecules in the atmosphere that sunlight hits and excites. Well, not perfect either, but the polarization will be the same. So every molecule in the atmosphere emits an electric field with a donut-shaped amplitude, like a dipole. So finally, here we are, standing on Earth, looking up at the sky. What do we actually see? Sunlight travels through the atmosphere and excites these tiny dipoles, molecules vibrating in many different directions. But here's the important part. Each dipole can only oscillate in directions perpendicular to the direction the sunlight came from. In other words, the dipole moment is always transverse to the incoming light. The electric field can only excite dipoles along itself. And this is actually the most important point. You can pause the video and think about it. It is somewhat sophisticated, so let us consider only the point in the sky directly above us. So dipoles are excited along the electric field, and the electric field is perpendicular to the direction of propagation. So the dipole molecule may be excited here like this, or like this, or this. And now these molecules emit light that propagates to our eyes. And that is what we see when we look at the sky. A horizontal dipole will radiate light in the directions like this, including downward, towards us. We see this electric field and we know the polarization. It is along the dipole. But a vertical dipole doesn't radiate downward at all. It only sends light sideways. So we cannot see anything. Well, almost. And there are other more sophisticated cases, but in general the polarization is still mostly horizontal. And we can actually see this in real life. Just grab a pair of polarizing sunglasses and look at the sky on a sunny day. The sky isn't perfectly polarized. There is contribution from some other dipoles, and your sunglasses aren't perfect polarizers either, but even so you will notice the effect. There is definitely some polarization in the sky. But this kind of well-defined polarization only occurs at that particular point in the sky. In the same way, you can consider any other point in the sky. There will even be points with no polarization at all. At least if the Earth were transparent and we could see the whole celestial sphere, simply because of the Hubble theorem again. So the direction and even the amount of polarization will vary depending on where in the sky you look. Let me also briefly mention why the sky appears blue. It turns out that these tiny atmospheric molecules are much better at scattering blue and violet light than yellow or red light. Light with shorter wavelengths is scattered better. But what does it mean, scattered better? It means that blue light is more likely to deviate and eventually reach our eyes, while red light tends to keep going straight and just pass by. So we see a larger amount of blue and a smaller amount of red. At sunset, things change a bit. Light travels straight from the sun through the atmosphere and reaches our eyes. Along the way, it gets scattered by air molecules in different directions. And as we've already seen, blue light scatters more, while yellow or red light scatters less, and a larger amount manages to reach our eyes. This was the first part of the video. But here's the fun part. You can actually recreate all of this at home. Use a flashlight as your sun and shine it through some liquids. People often suggest dissolving a bit of milk in water, but I've noticed the effect is also present in micellar water or some deodorants. I will be demonstrating it using my kettle. I just changed the filter and for some reason something happens that makes this effect nicely visible. I have no idea what's inside my filter or what's wrong with my water. Look here. When I shine the light from the side, the beam looks slightly bluish and it's also polarized, just like the real sky. But when I shine the light from behind, It looks more yellow, kind of like a sunset. If you found this interesting or learned something new, please support the video with a like or subscription. It really helps others discover it and helps me to stay motivated. And now a couple of things I have to mention. First, you might ask, why isn't the sky purple? Violet light has the shortest wavelength. But the answer is simple. We have to take into account the sun spectrum and the sensitivity of our eyes. But if you're overthinking things, you might ask an even more fantastic question. Why isn't the sky black? After all, aren't there enough molecules in a small volume to cause destructive interference and cancel everything? That's a tricky one. According to a course from Berkeley, it's due to fluctuations. You can check it out there. Did I forget to mention something else? Then write it in the comments.